So welcome to the topic complex analysis. Complex analysis is the study of functions that lives in the complex plane. That is functions which have complex arguments and complex outputs. So we already studied about complex numbers and complex function and their properties. Here we can study more about complex plane and function of complex variable, function of a complex variable. So let us start with a stereographic projection. In geometry, the stereographic projection is a particular mapping that projects a sphere onto a plane. The origin of the polar and stereographic projection was started in the period of Hipparchus. He introduced this mainly for astronomy purpose, but after we use it for our complex functions, complex analysis. A sphere is projected into a plane. The extended complex plane is the complex plane with a point at infinity attached with it. This is called a Riemann sphere and is denoted as C infinity. C union infinity, that is C infinity. And these points on this plane is mapped onto points on the sphere is mapped onto points on the plane, and vice versa also. We can consider how this projection is going. Stereographic projection, that mapping relates every point on the surface of the sphere with points on the xy plane. Consider a plane that divides the surface of the sphere equally. This way. Let capital N is the north pole with the coordinate 0, 0, 1. For a point Z on C, consider a point Z on C, a straight line, we consider a straight line through Z, small z, then N intersect the sphere exactly at one point, suppose it is capital Z, then it is not equal to capital N. Likewise, if mod Z less than 1, then the capital Z is in the southern hemisphere. If mod Z is equal to 1, then capital Z is in the value itself. It is equal to small z itself. There is no other mapping, that will be that point itself. And if mod Z is greater than 1, then all those points, capital Z is in the northern hemisphere. If mod Z is greater than 1, then Z is in the northern hemisphere, and if mod Z less than 1, then Z is in the southern hemisphere. Using equation of line joining points capital N and Z, we can find out that x1, y1, z1 values in the plane. That is, x1 will get from the equation, x1 is 2 into real part of z by mod z square, and y1 is 2 into imaginary part of z by mod z square, and z1 will be from mod z square minus 1 by mod z square plus 1. So if the given point which is in the sphere, then we have to find points on the plane. So by applying this equation, you will get the value of x1 as 2 by 5 and y1 as 2 into root 3 by 5 and z1 as 3 by 5. And in the vice versa also, given 3 points in the sphere, that is x1, y1, z1, you have to find out z value. Z is equal to x plus iy. So you have the equation z is equal to x plus iy. So using x equal to x1 divided by 1 minus z1 and y equal to y1 divided by 1 minus z1, you will get the answer as minus 2 and minus 1. X equal to minus 2 and y is equal to minus 1. So corresponding to 2, 1, 2, the point in the plane is z is equal to minus 2 minus I. If a1, if an is in the complex plane for every n greater than or equal to 0, then for the infinite series of complex numbers, sigma n is from 0 to infinity an. That is, the series is a0 plus a1 plus a2 plus etc. an plus etc. Then the sum of the first n plus 1 term is given by Zn is equal to a0 plus a1 plus etc. an. Then the sequence of the sums z0, z1, z2, z3 etc. zn is the sequence of partial sums of the series. As n tends to infinity, there are some possibilities. The sequence converges to a complex number z. In this case, the series sigma n is from 0 to infinity an is said to be convergent and has sum is equal to z. In this case, sigma n is from 0 to infinity an is z itself, and the sequence does not converge but tends to plus converge or minus converge, minus infinity, as n tends to infinity. In this case, a series sigma an is said to convergent, is said to be a convergent series if the given sum of partial sums, the given sequence of partial sums converges, that converges to a number z. Then we can say that series convergent. And the sequence of partial sum doesn't converges but tend to plus infinity or minus infinity, then we can say that series is divergent and it has no sum. If both the cases, if the series not converges and it is not diverges, then we can say that series is an oscillating series. Example, discuss the convergence of the series 1 by 2 plus 1 by 4 plus 1 by 8 plus etc. Check whether it converges and also find the sum of the series. So we have the series can be write as, this is of the form sigma n is from 1 to infinity 1 by 2 to the power n. So you know the sum of the series is, by using the equation, we have it is 1 by 2 into 1 minus the difference 1 by 2 raised to n divided by 1 minus 1 by 2. That is 1 minus 1 by 2n. As n tends to infinity, this term will goes to 0. 1 by n term goes to 0. So the limit is 1. So the series is convergent and its sum is 1. And what we can talk about this series 1 plus 2 plus 3 plus up to going infinity? Yes, the series diverges because the sequence of partial sums z0 is 1 and z1 is 1 plus 2 3, z2 is 6 etc. It is going up to infinity. So its limit is infinity Therefore, limit of the partial sum is infinity. So the given series is divergent. And what we can tell about this series? Minus 1 raised to n plus 1. The partial sum will give you plus 1, minus 1, plus 1, minus 1. So it is oscillating. So this is an oscillating series. It doesn't converges and doesn't diverges. It is an oscillating series. A power series is in powers of z minus z0 is an infinite series of the form sigma n is from 0 to infinity an into z minus z0 raised to n. That is a0 plus a1 into z minus z0 plus a2 into z minus z0 the whole square plus etc. Where this a0, a1, a2 etc. are complex constants and z0 is called the center of the series. If z0 is 0, the center is 0, then we have the power series is sigma n is from 0 to infinity a n z raised to n. Now what we can tell about the convergence of a geometric series? If an belongs to a complex number, it's a complex plane, for all n greater than or equal to 0, the series sigma n is from 0 to infinity an converges to a point z if for every epsilon greater than 0, for every arbitrary epsilon greater than 0, there exists a positive integer capital N such that modulus of the difference between the series and that point is very less than that our epsilon value. That is modulus of sigma an minus z is less than epsilon for every n greater than or equal to n. Above this particular value, the difference between a series an and that z value is very less. They are very close. Then we can say that the series is convergent. And the series sigma an converges absolutely if sigma modulus an converges. Its absolute value converges. Absolutely convergent implies convergence of the series. And if mod z less than 1, then limit of n tends to infinity z raised to n. If z is less than 1, then that limit goes to 0. Then it have a limit. So we can say that geometric series sigma z raised to n is convergent and which converges to the value 1 by 1 minus z. And if mod z greater than 1, what happened to the limit? When limit of zn goes to infinity. So the geometric series diverges. We have a theorem for a given power series sigma an z minus a raised to n. Define a number r such that 0 is number is between 0 and infinity and the number is defined as 1 by r equal to limit supremum of modulus an raised to 1 by n. That number r is called radius of convergence of our power series. If 1 by r equal to limit supremum modulus an raised to 1 by n, if modulus of z minus a less than r, then our series is converges absolutely, means convergent. If modulus z minus a greater than r, then the given series become unbounded and so the series is diverges. If 0 less than r, then the series converges uniformly on z. Moreover, the number r is only the number having the properties this. They converges if it is less than r and diverges if it is greater than r. And the number r we called as radius of convergence of our power series. If the power series a sigma an z minus a raised to n is a power series with radius of convergence r, then if r equal to limit of modulus an by an plus 1, if this limit exists, then sigma n is from 0 to infinity n factorial z raised to n. Its radius of convergence of this kind of series is 0. By applying this one, you can find that its radius of convergence is 0. And if it is the series is sigma z raised to n, then the radius of convergence is 1. And the series is of the form sigma n is from 1 to infinity z raised to n by n, then its radius of convergence is 1. For sigma z raised to n by n factorial, its radius of convergence is infinity. We have what is called an analytic function. Yes, if G be a given open set in C and f is a function from G to C, that open set to the set of complex plane, then f is differentiable at a point A in G if limit h tends to 0, f of a plus h minus f of a whole divided by h exists. If this limit exists and the value of this limit is denoted by f dash of a, and we call it as derivative of f with respect to at the point A. If f is differentiable at each point of this open set G, then we can call that f is differentiable on G. If the limit exists, then f is differentiable at the point A. If it is differentiable all the points in that open set, that is differentiable on that entire open set. A function f is analytic if f is continuously differentiable on G. Chain rule. Let f and g be analytic on g and omega, two open sets, and suppose f of g is contained in omega, then g composition f is analytic on g and g composition f dash is g dash of f of z into f dash of z for all z in G. And we have Cauchy-Riemann equations. As all you know, f is the given function, analytic. If f is analytic and u and v be the real and imaginary parts of that analytic function, then we have, yes, if the partial derivatives exist, then that must satisfy the Cauchy-Riemann equations. How will we find that? Let us evaluate the limit. F dash of z is equal to limit h tends to 0, f of z plus h minus f of z by h. As h tends to 0 along the real line, we will get an equation. So as h tends to 0, we have f dash of z is equal to dou u by dou x plus I into dou v by dou x. If h tends to 0 along the imaginary line, then f dash of z you will get as minus I dou u by dou y plus dou v by dou y. Equating both these equations, you will get the CR equations, that is dou u by dou x equal to dou v by dou y and dou u by dou y equal to dou v by dou x minus dou v by dou x. This is known as the CR equations or Cauchy-Riemann equations. A theorem, let u and v be real valued functions defined on a region G, and suppose that u and v have continuous partial derivatives, then the function f is from G to C be defined as f is equal to u plus iv, which is analytic if and only if u and v satisfies the CR equations. If and only if u and v satisfies the CR equations, then f is analytic. Let G be either the whole plane C or some open disk. If u is a function from G to R is a harmonic function, then we can say that u has a harmonic conjugate. that is V. U has a harmonic conjugate V. There is another theorem. If f is a function from G to C is analytic, then f preserves angles at each point z0 of G where f dash of z0 is not equal to 0. That is, a function which has an angle preserving property and the limit of modulus f of z minus f of a by modulus of z minus a exists is called a conformal mapping, a mapping that preserves both the angles and direction. Both the angle and in direction. So, we can say that such kind of mapping is a conformal mapping. If f is analytic and f dash of z is not equal to 0 for any z, then f is conformal. The converse is also true. F is analytic and f dash is not equal to 0, then f is conformal. Mobius transformation or bilinear transformation. Mobius transformation, or its another name is bilinear transformation. A mapping of the form S of z is equal to Az plus b by cz plus d is called a linear fractional transformation or bilinear transformation or Mobius transformation. If a, b, c and d also satisfies ad minus bc by if AC minus AD minus BC not equal to 0, then S of Z is called a Mobius transformation. And if S of Z is of the form Z plus A, then we can say that this S is a translation. That mapping is a translation. If S of Z is equal to AZ for A not equal to 0, then S is called it is a dilation. And if S of Z is of the form e raised to I theta into Z, then S is a rotation. If S of Z is 1 by Z, then S is called inversion. Z is a fixed point of the transformation A if A of Z is equal to Z. If A of Z is given as a Z square plus 1, then compare it with Z, then you will get the fixed point. Let Z1, Z2, Z3, Z4 be points in C infinity and define S as a function from C infinity to C infinity by S of Z is equal to Z minus Z3 by Z minus Z4 all divided by Z2 minus Z3 minus divided by Z2 minus Z4. If Z2, Z3, Z4 belongs to C infinity and S of Z is of the form Z minus Z3 by Z minus Z4, if Z2 equal to infinity and S of Z is equal to Z2 minus Z4 by Z minus Z4, if Z3 equal to infinity, in all these such cases, we have S of Z2, S of Z3 and S of Z4 values as S of Z2 is 1, S of Z3 is 0 and S of Z4 is infinity. We have a proposition that is if Z2, Z3, Z4 are distinct points and T is any Mobius transformation, then Z1, Z2, Z3, Z4 equal to T of Z1, T of Z2, T of Z3 equal to T of Z4 for any point Z1. That is, the linear transformation is invariant. The bilinear transformation is invariant under Mobius transformation. So our bilinear transformation is invariant. T of Z1 will be Z1, T of Z2 will be Z2 and T of Z3 will be Z3, T of Z4 will be Z4. So the transformation values will be same as the values itself. So it is invariant under bilinear transformation. And we have under a Mobius transformation, that takes circles onto circles and lines onto lines itself. So let mod z minus z naught is equal to C is equal to R, the radius, be a circle in C, and let W is equal to 1 by Z. If mod z minus z naught is equal to R, then we have modulus of z minus z naught raised to 2 is R square. So that implies when we apply z is equal to 1 by W value, you will get the answer as it is modulus of W minus z0 bar divided by z0 square minus R square by mod z0 square minus R square. So you will get the value as a 0, which is an equation of another circle in W. When you expand this one, you will get it an equation of circle itself. So a Mobius transformation takes circles onto circles. Similarly, for lines onto lines, straight lines onto a straight line.